Are we ready? Okay. Yeah. Distinguished Professor Van Speybroeck, ladies and gentlemen, on behalf of the Department of Chemistry and the Norwegian Chemical Society, I have the pleasure of wishing you all welcome to the Hassel Lecture for the year 2023, which is in number the 15th in the series. The lecture will be given by Professor Van Speybroeck from University of Ghent. Also, I would like to thank our co-organizing partner, the Science Library, and namely Lynn-Katrine Hirschti, Caroline Moe, and Dag Bakker for providing support in the preparation of today's event. Before introducing Professor Van Speybroeck, I would like to give a short biography of Nobel laureate Professor Odd Hassel of this chemistry department. The lecture series was inaugurated in 1967 on the occasion of Hassel's 17th birthday. Professor Hassel, who was born on May 17th in 1897 and studied in Oslo, where he received his real fag, degree in chemistry in 1920. Later, he went to Berlin to the Kaiser Wilhelm Institute in Dahlem to conduct X-ray crystallographic work. He obtained a doctoral degree from Berlin University in the year 1924. He returned to Oslo to work as an Universitetsstipendiat at University of Oslo from July 1925. 1 year later, he became docent of physical chemistry, and in 1934, he became professor of physical chemistry at the University of Oslo. He stayed at this university for the rest of his career and life. Hassel published a large number of papers in structural chemistry. During his very first years in Oslo, he dealt with problems from inorganic chemistry. From 1930 and onwards, his work concentrated on problems connected to molecular structure, in particular his pioneering work on the conformations of cyclohexane and derivatives. And this is why we torture our students to learn that conformation every time. His first groundbreaking paper in this area was published in 1943, and the final crystallographic refinement was ready in 1947. In later years, he also made seminal contributions to the structure of charge transfer complexes. Professor Odd Hassel was awarded the Nobel Prize in Chemistry in 1969 for his work on the structures and conformations of organic molecules. He shared the prize with Sir Derek Barton, Professor of Organic Chemistry at Imperial College, London. Professor Hassel passed away on May 11th of the year 1981. It is in his memory that this lecture series continued. The selected Hassel lectures were initially structural chemists working on areas more or less connected to Professor Hassel's activities. But in more recent years, a broader range of chemistry has been invited. This is in accord with the chemistry's constant development to tackle rising challenges in our modern society toward the more efficient and cleaner chemical processes, as you will most certainly be apparent from today's lecture as well. And now, a few words about today's Hassel lecture. Professor Van Speybroeck is full professor at Ghent University and head of the Center of Molecular Modeling, a multidisciplinary research center of about 40 researchers. She graduated as engineer in physics at Ghent University in 1997 and obtained her PhD in 2001 on a subject dealing with theoretical simulations and chemical reactions with static and dynamic approaches. Veronique Van Speybroeck has a record in significant contributions in the field of modeling nanoporous materials for catalysis, adsorption, For example, Zeolite Metal Organic Frameworks, Covalent Organic Frameworks. All publications are inspired and performed in close synergy with experimental groups. She received 2 ERC grants, the starting grant in 2010 and consolidator in 2015, which were strong drivers for new method developments in the field of nanoporous materials. After developing calculations of accurate chemical kinetics for reactions taking place in nanoporous materials, she also pioneered the simulation of complex catalytic conversions at operating conditions using enhanced molecular dynamic simulations, capturing the full complexity of the free energy surface. Currently, she is exploring methods to simulate materials with inclusion of spatial heterogeneities, as the behavior of realistic materials may strongly affect the crystal size, morphology, presence of defects. Van Speybroeck has served in many boards to evaluate research, and she is member of various editorial boards and international networks. She is also elected member of the Royal Flemish Academy of Science and Arts of Belgium. Professor Speybroeck, without wasting more of your precious time, our audience and I look very much forward to your lecture, the Hassel Lecture 2023. And the title is Operando, Modeling of Functional Nanostructured Materials for Sustainable Chemistry, Nanosensing, and Clean Energy. The floor is yours.
Good morning or good day. So thank you for the kind introduction, and also thank you for appointing me the Hassel Lecture to come back to Oslo. I have been in Oslo in the past, but it's a while ago, so I'm very delighted that I can be back here on this prestigious occasion. And indeed, I will talk today about Operando modeling of functional nanostructured materials, so for a range of important applications. This talk today will be a little bit more broad. Tomorrow I give a more specialized talk. So let's first set the scene properly. Here we have a bold statement: nanostructured materials can help to shape the future. So what do we mean? So we see nanostructured materials all around, of course. So for example, if we have to make devices for solar cell applications and these kinds, we need good materials. Here you see a device that was constructed in the US in the group of Omar Yaghi to capture water from the air, also in dry areas. So materials can help to capture water from the air. It's also an important application with some new materials. Of course, we need to find also structures and materials to make chemistry sustainable, let's say. And then I'm also going to show you here the first movie. It's also inspired by one of our own projects we had in Ghent with some colleagues. So this is an example of a Diels-Alder reaction, which you can do, of course, in batch. When you do that in batch, and it's, of course, an important reaction for a lot of chemistries, what happens is that then you can also create a lot of waste, let's say. That is what we will see appearing here in a minute later. So this is also done under influence of light, so it's also photocatalysis. So it's done with a ruthenium complex. And so what we will see is that when you do it in this way, that you can create also a lot of waste, let's say, and we do not want this, yeah? And so for that reason, we also wondered whether we could do it in another way. And so our colleagues in Ghent tried also a flow reactor. And in this flow reactor, they embedded a material, let's say, and then that would become more efficient. That was the idea, basically, to do that. If you look here into the material that was embedded into the flow reactor, we already see here a very nice view of a nanostructured material. Here we can see the complex, the ruthenium complex, which is normally also done in homogeneous catalysis, but here it's anchored on a material. And then at a given moment, you will see, of course, that the reaction occurs. So that was the idea that we had. And eventually, that could lead to a more sustainable process, let's say. So that was done. It was with some success. The project has now ended. So we had perceived some good results. But of course, as research goes, there are always drawbacks. But this is a nice idea also to see where materials can be important. So a lot of my talk today will also go about nanoporous materials. So let us also clearly define what we mean with nanoporous materials. So here you see a chimney where, of course, a lot of bad flue gases come out of the chimney. And the idea would be also here to separate the good and the bad gases, let's say, from each other. And there also we can see usage of important materials. And so basically when we look a little bit more in detail, we can see here some sort of a filter, and the idea would be here to separate the CO2 and the nitrogen, and so basically then to do useful things, like with, for example, the CO2 from point sources, So basically here, this is a material, a filter material, and we can have a closer look now what it looks like. So then we start zooming into the length scale, basically. The first thing that we see is pellets, that we also can see with our eye, let's say. But then we are going to zoom further into the length scale, let's say. And the first thing that we see then is also crystals, which are then of the order of micrometer. This is for us still as modelers huge, or very big in our reference scale, let's say. So we are now going to zoom further into the length scale, and then we start seeing the atomic molecular scale. So this is our terrain, where we do modeling. So we go further. And then this is also an abstract representation of the material, as I will also use a lot during my this lecture today. So we can really see here materials with pores, and interesting things can happen in these pores, let's say. So there are quite some definitions. Of course, pores can be small, pores can be big. So there are conventions for that, as you can see here. But these are the materials that I will talk a lot about today. The first type of materials that I will talk about today are zeolites. Zeolites are everywhere around in applications. Maybe we are not aware, but they are everywhere around. So they are the workhorses for a lot of processes. Let's have a look how a zeolite looks also at the atomic scale. So we are going to zoom into the material. What do we see? So we see here, of course, a porous framework, as I already introduced, with silicon and oxygen, basically. And then this material can become very interesting when you create a defect. When one of the silicon atoms is, for example, replaced by an aluminum, you have a defect, and there are hotspots where things can happen, let's say. You also find them in nature, but of course today synthetically they are made, and there are approximately 240 zeolites today around, not so much if you compare it to other type of materials. And so we find them everywhere around, like, for example, in ion exchange applications, like, for example, here, or to remove some bad odors. So you also can find them. And, of course, in the classical petrochemical industries. So then you may say, maybe this is not so interesting anymore because we do not want these technologies anymore. But zeolites also find quite some applications in new technologies. So this is also taken from another project that we had with the colleagues in Leuven, which is the group of Cells, where they also make technologies to make from lignin, let's say, where we also have a large aromatic fraction here, oxygenated aromatic fraction. So they have developed technologies to depolymerize that to these building units here, which have these are oxygenated species. And then zeolites can also do the work there in more difficult conditions to then also functionize them to our building blocks that we need today everywhere around in our daily life, let's say. So here we see an application of a new feedstock where we start from biomass, and zeolites also there can do the work because they are very stable, they can work under varied conditions, so we will see them further also for new technologies. Another type of materials that I will discuss today, which is going to enter the scene, are metal organic frameworks. It's a completely different type of materials. They are not. They are around in the 90s. They became very famous, let's say. So these are hybrid materials made from this inorganic, so metal nodes, let's say, and also organic building blocks. So basically, it's like Lego. You have building blocks, and then you can synthesize the material, let's say. The point is that they are made from these building blocks. We can make a huge number of MOFs. So we have a huge database of MOFs around today. And so the question is, of course, there, what is a good material for a good application? This is, of course, a major question. So because we have seen, you can see here the principle of building. So then you again make such a nice frameworks, let's say. Here you can see the material is perfect. Of course, in reality, a material is never perfect. So this is a very simplistic view, I would say, on what the reality is. But in essence, we can make a lot of these materials too. You find them in all kinds of applications. It's a short overview here. Here is a picture also of a conference that was organized last year in Dresden. So it was the International Conference on MOF Frameworks, because in the beginning, these MOFs, they entered more the area of peculiarities, so interesting materials, but maybe not interesting for applications. But now we have also entered a stage where these materials also have become very important for important applications. As a result of that conference, we wrote a meeting report. So I did that together with my colleague, Guillaume Morin in Montpellier. And one of the statements that we made there is, so here we can see, since their inception in the late 90s, so they were first in the laboratory, maybe curiosities, but now they start to see their applications in many important fields. So a few cases where we can see that is, for example, these are materials that we cited there. Of course, there are only a few examples. There are many more. We can see, for example, that we have these materials. They have always special acronyms. So some materials are able to collect water from the air. Remember the device that we saw in the beginning slides that could take water from the air. So that was a MOF that was in there. Or another material, so this material, which can also take CO2 from the flue gases, also something that I already introduced already. If you look into the papers that are behind these technologies, we can also have a look at some of these materials here. So like, for example, the material that can take water from the air. We see here the isotherm, it has special points. And we can also see that it has special sites where indeed the water can indeed adsorb. Also modeling was there also crucial to unravel the insights why the material does the work. Yeah? Here we see the SCAF20 material, which is now also used on industrial scale. The reason why it is very good, because even CO2 is also captured also when you have a larger humidity. Yeah? This is also what we can see here on this scale. So we can see that it keeps also selectively taking the CO2 even under a higher humidity conditions. Yeah? So these are two examples. Now, so the interesting thing, why we are also interested in nanoporous materials, because we can highly tune these materials at the nanoscale, let's say. So let's illustrate that a bit. So this is, again, my pictorial representation of a nanoporous material. So basically what we can do, we can remove some linkers. So we can also replace some linkers by others. We can put some other sites in the material. And yeah, there are a lot of things that can happen. You can see the space, combinatorial space to do things with the material is huge. Of course, the question is, what can we do interestingly with these materials? When you have more choices in life, it's also the same. It becomes often more difficult. Yeah? And that's, of course, also the same with the materials. They can have various functions. So let's look at a few functions. So, of course, catalysis is one of the major functions that these materials can have. So basically what happens during a catalytic process, you send molecules over to the catalyst, they find a hot spot, and then if we are doing things right products are formed. Okay. For sensing applications, they can also be interesting. Again, we send molecules over to the material. If the material is not right, nothing happens, so the materials, so there is no interaction, but it could also be that, for example, the material is properly functionalized and it captures molecules. So that is an illustration of the capturing that I already shown you in the earlier slides, that some molecules could be captured. We can also have optical applications where we, of course, use light. Yeah? So here, for example, we send some molecules over the material, nothing happens, but if we use light, You have also seen it in one of my introductory slides. Of course, interesting thing can happen. We have photocatalysis. Yeah? Of course, we need to be able to also make these spots right, let's say, for the right application. Now, where does modeling fit in? Of course, I'm a modeler. I'm not an experimentalist. So obviously, I'm going to tell you something also about modeling. So when you do an experiment, basically what happens is you look from the outside. Yeah? So, for example, you send molecules over a crystal particle, and you see that something is formed. We see a green species, we see an orange species, but basically it's very difficult to know from experiment alone what happened under the material. Yeah? This is a top-down approach, let's say. What we do in modeling, we have a bottom-up approach. Yeah? So we look from the inside. Yeah? And so basically what we do, so we go back to our abstract representation. So we also send these molecules over the material, and we see, for example, that one molecule interacts here, one molecule interacts there, and so we can try to find these hotspots. And then we can also look at the nanometer scale, and we make nice movies, like, for example, we see an interaction of a methanol molecule with the Brunstad acidic site. You can also tune the material to do different things, like, for example, here, we can see this is a zeolite, which was post-synthetically modified with calcium species. We again have interactions of methanol, but it's, of course, a completely different active site. It will do completely different things, of course, yeah? But that's what we can do. So we can look really at the molecular level and see what happens. So it looks, it basically looks now very nice at this moment, but there is also a problem. Yeah? So if we compare this length and time scales of modeling with the experiment, we have basically a huge gap between these two. When we do modeling, indeed, we look at the nanometer scale, and we simulate, if we make these nice movies, of the order of 100 picoseconds, let's say. But that is in huge contrast to what experimentalists can observe. Even with the best spatio-temporal resolution, let's say, crystal sizes have the order of micrometer, and phenomena can take much longer than, of course, than the picoseconds. Normally, they take much longer. So there is a huge gap between these two worlds. The question is, how can we bridge this gap? For that to understand, we need to have a look at the typical modeling exercise. So the first step that we need to do is we need to define a structure. Yeah? So basically, and this is already one of the very difficult things. So materials are not perfect. It's of course, a very important statement already. As human beings are not perfect, nobody's perfect, so materials are also not perfect. This makes them interesting, by the way. Yeah? So here, for example, we see zeolite, abstract representation. We zoom in, we have some mesopores, we have maybe grain boundaries. We can also look at other materials, like, for example, the MOFs again. So we have a crystal particle. We can see here we can have some short-range defects. We can have mid-range defects and longer-range defects. This is all around, and it determines their function. Yeah? And it's important to account for that also when we do modeling. Otherwise, we do not have realistic representation of what happens in the real experiment, let's say. This is the first thing. Second thing, when we do a modeling exercise, we need to know how the energy of the system evolves in terms of the internal coordinates. So we need to have a notion of the potential energy surface. So here it is very simplistically shown in only 2 coordinates, let's say, but basically it boils down that we need to know what are interesting places for the system to be. So you can see here there are minima, there are other minima. So basically we need to be able to determine that. Yeah? And the way how we describe this is basically in the heart of the molecular modeling exercise. This determines the length and time scales we can access. In principle, if we want to do this right, we would have to do this by quantum mechanical techniques, so solving the Schrödinger equation. Yeah? Schrödinger equation looks like a very simple equation. If we look at this, it looks like a very simple equation. It's a very difficult equation to solve, yeah, for realistic systems. And we can do quite a lot today, but still, our length scales are thus restricted to these length and time scales that you can see here. So much too small to compare to experiment. There are various strategies to go beyond that. We can make classical force fields where we basically do not describe explicitly the Schrödinger equation anymore. Tomorrow I will talk more about that, so today I won't give technical details. So this is what people have done a lot. There is a new direction also coming up now, where also from these data that you have here, we also make machine learning potentials. So machine learning is also everywhere around in our daily life now. So it's also in our field around. So basically, we try to construct potentials that can describe this potential energy surface with the same accuracy as these data, but they are much more efficient. It's the idea. And then there is another methodology, which I'm not going to explain, where you basically abandon the atomic scale. And that determines the length and time scales that we can access. Then there comes an interesting point. Suppose you have the potential energy surface, okay? Then the point is how to explore that. You can do it very simplistically, and you can say, okay, I'm going to look here at a little bit around this minimum. So we look a little bit around, see what happens. So another methodology is that we already do molecular dynamics, so this particle can move a little bit a bigger space of phase space. But interesting becomes, like, for example, when this particle starts here, and it wants to go there. This is typically what happens with the chemical reaction. It needs to go over a barrier. And so basically, we see this movement, and we can also try to simulate that. You can compare it to such a height map that you might also use when you go hiking in the mountains, like, for example. So you start, for example, here, and then you can go to some other places. And of course, the big point is, how do I find interesting places on this hiking map? Yeah, it's a major challenge for us. It's a very multi-dimensional problem. It's important to not only look statically at the system, and I want to illustrate you with this movie also. Here you see again a zeolite. This is a blue spot where there was a Brunstad acidic proton. Remember, if you substitute a silicon with an aluminum, we have a defect. So basically here we have this blue spot. It's a Brunstad acidic proton. Now we are going to bring methanol molecules into the pores of the material. And then we can see that at a given moment, this Brunstad acidic proton is taken from the lattice. Yeah? And so it starts to walk. Yeah, so my active side basically completely changes. Yeah, and that is of course important to take into account that when we simulate materials, we need to simulate them at the conditions in which they do the work. Yeah, again, like with human beings, so we also function different depending on the conditions in which we are brought. Let's say for the materials, it's just the same. So this is basically this whole a set of techniques that we use. And so the question is, how do we solve the length-time scale gap? You might wonder, we have big computers nowadays. It's true. We have, of course, we are now entering also the era of exascale computers. So in Europe, we have only a pre-exascale computer now, but in the US and other continents, they are the first exascale computers that have been taken in operation from this year. Next year, normally, we should also have here in Europe an investment in the exascale computers. So there you can have 10 to the 18 this floating point operations per second. So that is the next generation of computers. Also here, we wrote together with some colleagues also a viewpoint, which just appeared also, on what exascale computing could mean for materials modeling. If you're interested, you can read. So it's a viewpoint of a few people. But I have taken a quote out of the article there. So here you can see, of course, we can make enormous progress with these extensive computers where we have CPUs, we have GPUs, and all these kind of things. It's all interesting. But the interesting sentence is here. Most of all, we also need innovative methods and algorithms. Yeah? So not just because we have the bigger computers that they will solve everything. We need also very good algorithms. Yeah? It's very important to realize that. So now, before moving on, we can also make an analogy, because it will be an interesting analogy also for some applications that I make later. So you remember that when we have the potential energy surface, you could compare it to a hiking map, let's say. I explained that to you. So now I'm going to make an analogy again with this mountain landscape. So basically, a lot of the things that you will see here will be transformations, physical transformations, chemical transformations, catalytic reactions. Basically, what needs to happen is here we have, and we can compare it basically to this scene that we have here. So we have people here, and so they want to go to here. Okay. They are very difficult paths, of course, which they will not take, and they will try to find the good paths in the mountain landscape. We can also see here that there is a lake here. This lake is, at these circumstances, not accessible for these people. So they cannot travel along this path. So you can see it's sunny, it's good weather here. Now, what happens if we change those conditions? So you can see they start to walk. So basically, if we change the conditions, it becomes, for example, very cold. Yeah, then we can see that the lake becomes frozen. Yeah, and so this is a new path that appears. So now these people, they can indeed cross this path. So this is also what happens indeed when we look at materials. Yeah, when the conditions are changed, other things happen. So we indeed need to evaluate them at the conditions in which they do the work. Yeah. Another thing that is important, that relates to the defects that I already said. So also in this mountain landscape, again, you can make, for example, defects. You can make a tunnel, and then you can go there. It's another pathway that appears also with defects. Okay. With time, the rocks that were here, they can come down. And basically, you can see it. These are, again, closed, basically, these gates. It's also what we see with materials, with time on stream. The material gets, for example, aged. It does not do the work anymore. So basically, then we are here. So you can see there are a lot of analogies with our materials that we use. So now let's illustrate some things with some real-life applications. So the first case is indeed the case of the operating conditions that I want to illustrate to you for materials design. So this is an application which is taken from this optical applications. Here you see there's a plot with, it's for photovoltaic devices, basically, where they make these charts, what are good materials have good efficiencies for photovoltaic applications. Of course, silicon is all around, but we can see that there are also new materials coming up, and these are the perovskites. And these perovskites, basically, they also start to have good efficiencies, basically. Yeah. And these are the materials that I'm going to look at now. This is in part of a collaboration with the group in Leuven, with the group of Johan Hofkes in Leuven. And so when you look at these materials, they have a nice structure, as we can see here with octahedrons. So this is perfect material, as we can see here. Now we are going to look basically on the nanometer scale, how they look like. And so perovskites have, of course, this structure, ABX3 structure. So in our case, this is cesium. Then we have lead here, and this is iodine. The purple things are iodine. So you can see here, it's a very well-structured material with octahedrons. Now we are going to use them also in optoelectronic devices, and also see, because the interesting thing is that this material, when it has this form, with these octahedrons, then it's optically active. Yeah. Now, what did our experimental colleagues do? So they deposited here this material. So this yellow layer here, yeah, is this the metal halide perovskite, which is deposited as a thin film on an underlying substrate, let's say. And then, so this is the material which has the right function, let's say, right optical application. So with some spectroscopic technique, it is used. So basically, we start here from this material where everything is right in place, yeah, with the octahedrons well connected. Then when we expose that to room temperature, let's say, what you immediately see is that these yellow spots appear here. And basically, the material starts to degrade in something else we do not want. Yeah? And so you can see here, if you look at the atomic scale, that this material transforms into another phase, let's say. And with time, it goes very quick, basically. We can see that you have all these big spots. And this material that we now receive is not interesting anymore for optoelectronic applications anymore. So, of course, then we try to find methods to stabilize this phase, basically. So here you can see some of the phases that were observed. So these are the optical active phases, so close to this nicely ordered material. You find them at high temperature. If you bring them at low temperature, so this is a thermodynamically stable phase here, we see this disorder phase, which we call the yellow phase. So there are two things to remember. We have the black phase here, which is the active phase, the one that we want, and we have the yellow phase, which is thermodynamically stable, which we find at room temperature. So what the experimental colleagues did is they found a strategy. So basically what they did, so indeed they deposited it on a thin film, let's say, on an underlaying substrate. And then what they did, so they made some patterns, micro-patterning here. So here you start basically from the thermodynamically stable phase, so the yellow phase. So that's the reason why it's yellow. So we make a micro-pattern here into in this thin film. Then we are going to increase the temperature to bring the material in the optically active phase. So that is what you can see here. Then, of course, we want to make this material, use this material at room temperatures. You cool down, and then they see that basically the material, thanks to this grid that was made to this thin film, that basically the material stays in the optically active phase. Yeah? What is the reason? It's very difficult to say. That is not one unique answer, but one of the reasons is that this material is strained here along these edges, and the strain of the micropattern ensures that the material stays stable in this octahedron phase, let's say. Then we also try to model that, of course. That is what you will also see in a lot of things that I will show. We always work closely together with the experimentalist. I think it's very important. So here you can see a free energy diagram. So this is the black curve, the black points here. This is the thermodynamics in case you do not have strain. The yellow phase, so this phase, is always more stable compared to the phase that we want. But if we induce strain, so and these are calculated profiles with strain, we can see that we can modulate this difference and make this other phase, this difference between these two phases more favorable for the applications. This is only part of the explanation, because this does not say us anything about the mechanism that leads us from one phase to the other. So, and that is the reason why we also thought maybe we have to also try to construct this free energy landscape, let's say. So this mountain hiking map that I also referred to earlier. So basically we start here from this nicely ordered structure, so the active phase. And then we can start to do some MD simulations, and then we can see that first we have a first movement where there's these units are displaced like this, and we have these arrangements like this. It does not go in one step. And then we do another, this molecular dynamics simulation, and finally it goes to this disordered phase. Yeah? So by doing these molecular dynamics simulations, we can try to unravel how this process brings us from one state to the other. It looks very simple here, like I presented here, but it's really a huge challenge to find good coordinates and find good paths to lead you to all these minima, because there are many, many minima for this material. It's really not fully resolved. So this is the first example where you can see operating conditions are important, and you can also try to understand what happens for and try to tune the material for interesting applications in close synergy, I would say, with experimental people. The second point is about metal organic frameworks. So here we are going to illustrate. So remember that there was a huge length timescale gap between what we model and what the experimentalists do. So, and here we are going to stretch the simulations and to see how far we can go. How close can we get to the experimental measures, let's say, and length scales. This is what we are going to do here. This is an illustration from flexible metal organic frameworks. So some of these materials have very interesting properties in the sense that when you just expose them to external stimuli, like for example, you expose them to pressure, to a gas pressure, or to temperature, then you can see that suddenly this material changes shape. It goes to another phase. So these are also sometimes called soft porous materials because they go from one phase to the other. It's, of course, very interesting, a property that they have because they can be used then in sensors. So they respond upon an external stimuli, let's say. So that is a very interesting property. And of course, there have been huge efforts in the field to try to understand this. The prototype material that does this is this MIL53 material. As you can see, these materials have all very fancy acronyms, so depending on the laboratory where they were made, and so we cannot explain that in detail here. So, but basically, we start here from a material which is open, yeah, and then at a given moment, it can close. Experimentally, you can try to follow that. So basically, here you can try to measure also the volumes, let's say, or the adsorption isotherms in terms of the stimulus. So like, for example, here it is in terms of the temperature. So we can see this is closed pore phase, and then it can open, and then it maybe can return. We can also see for pressure, so that you have these typical hysteresis curves. Also for gas adsorption, we can see that we have typical hysteresis curve. So that is what they can clearly observe experimentally, whether the material breathes or not, whether it opens or not. Yeah. Then we can also try to understand that from modeling point of view. And so the first point that we do is we try to construct these free energy profiles in terms of volume. So volume is important. When the material is open, the volume is, of course, we are here. If the material is closed, we are here. And so we make these movies. You have seen quite some movies now already. So we can make these movies again of a perfect material at this moment. So this is how we started in the beginning. So you can see this breathing motion. So that is interesting. And then you can try to compare that to the experimental curve. So that is under influence of pressure. It's an empty framework here. So this is what you can see from experiments. So it's a volume versus pressure, this diagram. And so here you can see you start big volume. So you apply pressure, basically, and it can close the material. And we can indeed also construct, we can construct this, but we can also construct the free energy diagram. We see two minima here. Yeah. The interesting thing is then, can we modulate this behavior? So can we change the material that maybe it has different properties under the applying of the pressure, let's say. When you look at it experimentally, at these volume versus pressure curves, most materials will behave like this. Yeah, so they have, like, say, an ideal spring-type behavior. So if you put pressure, it will contract a bit, but then it goes, of course, back to its original phase. These materials that we are discussing now, so they do a phase transformation, as I already explained. Sometimes it is the case that they go to small pore phase, and they stay there. They never return. Sometimes it is the case that they go to the closed pore phase, but then they can go back. It's reversible. Yeah, so you can tune this. Here we can see some free energy profiles that we constructed over the years, let's say. So this is the MIL53 material you already have seen. So by the way, we have here an aluminum-based material. So we have an aluminum oxide chain, which is basically perpendicular to the well, not the board, to the screen, yes, to the screen, yes. So this is the aluminum oxide chain, let's say. And then we have these organic linkers, which you can see here. Okay. When we introduce, like, for example, fluor into the framework, we can see that we can change the shape. Still two minima, but it's different. It will have another behavior. If we, for example, put here gallium at these metal nodes, we can see that there will be no breathing anymore. It behaves like a spring. If we use another linker, like, for example, here we use another linker, we can see that it will become reversible breathing, open and closes. Yeah? So you can really see that you can modulate this behavior by playing with the building blocks. And that is also something that I said in the beginning. We can make a lot of MOFs, an enormous amount of materials. The interesting thing is to know which materials can we make for the right application. And also here you can see one of these materials, so that really does a big contraction. If you apply pressure, and these are, of course, interesting for mechanical applications. They can store mechanical energy then. Yeah. that is all interesting, but experimentally it was also observed that this behavior that I explained now is critically dependent on the crystal size. Yeah? One of the earliest reports that showed this was this paper that appeared in Science. So basically, we start here from this material which has micrometer-sized crystals. What they see is, so they start in the closed pore phase. They do gas adsorption. The material opens. But then it seems that when you remove the gas, the material discloses again. So you have reversible behavior. Yeah? Now we are going to downsize the material, yeah? To meso-sized crystals. What do we see? We start from closed pore phase. Gas molecules enter, the material opens, and then we remove, indeed, the particles again, but the material stays open. So it's not reversible anymore. So this behavior is critically dependent on the crystal size. This was one of the earliest reports, but by now, there are many other reports that have seen similar things. And of course, there have been huge efforts to also understand this. And so, of course, we were also intrigued, tried to see, can we understand this? Then I go back to one of my earlier pictures that I have shown. So here you can see a crystal particle, as we would want to simulate it. Yeah. So basically here you can see a finite-sized crystal. You can have defects and so on. So basically, ideally, we want to simulate that. Of course, if you want to simulate that, you cannot use quantum mechanical techniques because you do not reach length scales that you want. So the first thing that we did is we constructed classical force fields. So they allow to go to larger length and time scales. So we are in this area of the figure. So remember, the potential energy surface is at the heart of the molecular modeling exercise. This determines accessible length and time scales. Yeah? So we are going to use here classical force fields, which we developed ourselves in our group. And so we start small. This is what you have already seen. So we start from some small unit cells or supercells, and we can see these movies we have already seen. So you can see that nothing breaks in the material. So this is typical for the classical force fields. They do not allow things to break. Yeah. So they are classically parameterized, so bonds cannot break here. Yeah. But we can make these movies. So then we said, okay, let's increase size. How far can we go? So we're going to start to increase the size of the system, basically. And then at a given point, that was in 2019, yes. So we went to crystal sizes of about 10,000 atoms. Okay. And then we do the same exercise again, and we try to see whether we see other mechanisms depending on the crystal size, let's say. I'm going to use here this visual representation to guide you through. So basically, remember that we have an aluminum oxide chain perpendicular to the screen. If you see red, the pore is open. If you see blue or you see green, the pore is closed. Yeah? So you remember, you can have an open pore phase, you have a closed pore phase. If you have closed pore phase, it can also be in two directions. It can be in this direction or it can be in this shape, let's say. So let's see what happens. If we do simulations on small systems, then we can see that everything collapses cooperatively. It's normal that we see that, because then our system is so small, you cannot allow disorder in this system. Yeah? So basically, here, the system is so small that you simulate, you have no disorder. You do not allow disorder. Yeah? This is typically as a result of the simulations. Now we are going to increase size, and what we can see here is that the transition mechanism changes. We see now a layer-by-layer transition. So a lot of disorder is introduced into the system, yeah? And now we see it, because our system is now big enough to see it. Earlier it was too small, we could not see it, yeah? This behavior. So this is for the simulations with 10,000 atoms. Then we were not really satisfied. We said 10,000 is good, but maybe we have to go to bigger crystal sizes. And so we wanted to go to 1 million number of atoms. Yeah? For that to happen, we used very efficient techniques from also biochemistry field, biosimulations. We are, of course, used to do very large simulations. And so we went to 1 million number of atoms, and then we are going to look again at the movie, and it seems then that even then you can induce other transition mechanisms. Yeah, so here you can see that things happen at nucleation points. We can have strong deformations. Yeah, so and you can also see formation of domains here. Yeah? And so you clearly see that depending on the size of your crystal, you can see other dynamics. For that reason, also the terminology spatio-temporal evolution has been introduced in the field, where the dynamics is affected by the spatial extent, or the spatial dimension, let's say. Length and time scales are correlated, let's say. So this is what we did here. This was still with classical force fields. Now, today, I'm not going to explain that. I'm going to explain that tomorrow. But basically, we have now also very recent results where we also do that with machine learning potential. So this is a very recent movie. It was made last week, I think. So, so here you can see, again, similar simulations, but all done with machine learning potentials, where you can also see this order taking place. And that is, of course, the way forward, because then we can also simulate, for example, breakage of bonds and so on, but I will explain tomorrow. So what we see here, size matters, yeah, for these simulations. So ideally, we want to simulate such a real crystal to connect with experimental observations. We are not yet there, yeah. We need to do other things yet to reach that. It's a huge challenge, but we can try to understand in synergy with experimental people what happens, basically, yeah. Third case is in catalysis, zeolite catalysis. Yeah, yeah. The examples that I will touch upon are taken. Yeah, we have worked a lot, and of course here in Oslo also they have worked a lot. We have for a long time very good collaboration with the people here in Oslo on this on the methanol to hydrocarbons process, but also recently on CO2 to hydrocarbons process. And these are, of course, interesting processes, because here you start from other feedstocks like methanol and also CO2. Of course, we want to make our chemicals in another way, so not from fossil components, let's say. So basically, we can start from methanol, we can start from CO2, and we can try to make the building blocks that we need, let's say. And zeolites are very interesting to do that. So that's the reason why we have looked at this. Yeah, of course, that is something you know, of course. We are always looking at ways to to make this ethene and propene. There is always a rising demand for these components. And so we need to find innovative ways to find these building units. Yeah. So indeed, CO2 might be interesting. You have also seen in the beginning of the presentation that CO2 might also be captured at point sources. If we could do interesting things with the CO2 and then convert the CO2 with interesting components, that would be a very interesting route, let's say. And that is something that is explored. So basically, if you start from CO2, you can convert CO2 first to methanol. And then from methanol, you can indeed go further with the zeolite catalysis, with the MTH or MTO process, and you can make the hydrocarbons here. You can also, with the CO2, here you, of course, need the metal oxide catalyst. You can also start from the CO2, do the reverse water-gas shift reaction, and then do the classical Fischer-Tropsch, and then we can also try to tune the product distribution that you receive from Fischer-Tropsch with zeolites, and also make selectively the hydrocarbons that we want. So here we have this zeolite catalyst. The interesting thing would be if we have a tandem catalyst which can combine these two things, where we can go from CO2 to these components in a selective way. So that would be very interesting, and a lot of people are looking into that. So major questions that we have here is, how can we tune the activity, selectivity of this process? Can we increase the lifetime of the catalyst? These are also typical questions that we always receive. Now, catalysis, and also, of course, zeolite catalysis, is an immense, difficult problem to model. Yeah, because it's the prototype example of a multi-length timescale phenomenon. Yeah, here we can have a very simple representation of what happens. So we have some species, they come from the outside. The first thing that they need to do, they come to the surface, then they need to enter, then they have to move, find their way there, diffuse, adsorb, and then at a given moment they find a good place to do something interesting, and then the products are formed, and they need to go define their way out, basically. This all happens at completely different length and time scales. It's a problem that we have to model that. So the first thing that I will try to illustrate to you is that it is also very important when we look at these processes that we again look at operating conditions. As I already illustrated again, also here it is very important, yeah, because some of these processes happen at higher temperatures and so on. So let's illustrate a little bit what we found here. So this is work that we done together with the group in Kous, with Jorge Cascon, on this bifunctional catalyst for CO2 to hydrocarbons conversion. So we have a metal component, we have the zeolite component, and so what they found a very good catalyst to selectively transform the CO2 indeed to the hydrocarbons. So they came to us because so this is a little bit more in detail the chemistry. So here you can see the reverse water gas shift reaction, and then the Fischer-Tropsch, and then here is the zeolite. Here you have the longer hydrocarbons, which you can selectively make this ethene, propene, aromatics. And what they found is that if you use a particular zeolite here, you can selectively form these small alkenes, or you can selectively form the aromatics. They use two types of zeolites to do that. First of all, they use CSM5, as we all know, of course. So here we see the structure of CSM5, and it has this particular channel system. We have the 10-ring straight channels. We also have the sinusoidal channels. And the other zeolite that they used, this was the mordenite. And mordenite is much more complex. So we have cages, so we also have channels. So it's much more complex. You can see here we have 12-ring straight channels. So we have there smaller straight channels. There are side pockets, and so on. And what they saw is that, what they saw with ZSM5, basically they saw that ZSM5 selectively made aromatics, and mordenite selectively made olefins. Yeah, and so they came to us. Can you give a molecular explanation? We see it, but we don't understand it. Yeah, of course. Again, this is part of the story that I'm not going to tell you. It's a very complex story, and that is interesting because I want to point you to the fact that we need to evaluate species at the conditions in which they do the work. Yeah, so if you look at these larger hydrocarbons, so alkenes, so we start there, so it's nonene that you can see here. When you have nonene and it adsorbs in the zeolite, there are 4 species that can be made. We can have a free van der Waals complex, we can have this pi complex, we can have a carbenium ion, and this is the interesting ion that we need because the carbenium ion will lead to reactivity. And we can also have alkoxide. If you look in the literature, many people assumed that when you do this adsorption, these species form alkoxide, where you make this bond with the zeolite. Yeah? These were simulations that were done at 0 Kelvin. No dynamics, sometimes with smaller clusters and so on. Okay. So these are the interesting species that we need to do reaction. So what we did then, we did some of these MD simulations, and this is in mordenite. Here you see nonene. And what we can see, it starts somewhere in the side pockets, and then when the simulation proceeds, we can see that it's not active. It just goes into the straight 12-ring straight channel, and it stays there. It's completely inactive. Yeah? So it will not form an aromatic species afterwards because it's not activated in mordenite. If you look at ZSM5, we see a different story. So here we start again from this nonene, and basically at a given moment you will see that, so here is the Brunstad acidic proton. You see the risks clearly in interaction, and it will indeed form here carbenium ions. And so ZSM5 has there's the potential to form carbenium ions, and then from these carbenium ions, it can make indeed also aromatics. So that's part of the explanation why ZSM5 made aromatics and the other did not make aromatics. Yeah, but very important, if you do this, you need to start from the right intermediates, and you need to evaluate that at the right conditions. So that's a very important application where we are now also working in close collaboration with the group of UNI here in, yes, so we have many work discussions on this topic. It's a very difficult topic to understand. The next thing that I want to show you is, because this is a multi-length timescale process, can we also model this diffusion when species diffuse through the lattice? Because diffusion is normally a longer length scale process. So this was indeed inspired also by the methanol to hydrocarbons process. So we are here. We are here in this block, let's say. So yeah, also a very difficult process to understand. So many studies have been done there. If you look at this process, what happens is we start from methanol. What first happens is we have an equilibration phase where we form dimethyl ether and water. So it's what happens here. Then there is an induction phase where we see the first formation of the first hydrocarbon pool species, which of course seminal work has been done here in Oslo. So we always refer to many papers here of very good work that has been done here in Oslo to understand this. And then we come to the real active catalyst. And the real active catalyst, we can see that hydrocarbon pool species are embedded into the zeolite. And basically, this is the catalyst that we want. So we also need the Brunstad acidic proton, but we also need these other components. Otherwise, we do not have the active catalyst. So you can see it's a very complex catalyst. Yeah? And of course, with time on stream, the catalyst can also deactivate. So remember my mountains with the rocks that came down. So basically, here you can compare that to a deactivated catalyst. So here, these hydrocarbon pool species have aged and they block everything. Yeah. What they also saw with time on stream is that in a catalyst, it was a catalyst with cages. It was SAPO 34 catalyst with cages and small windows. They saw that with time on stream, does the selectivity for ethene increased? And so the question is this due to the cause of reactivity, or is this due to the cause of transport? Yeah? And so that is the reason why we then started to try to understand, can we understand this transport of these molecules through this zeolite system, let's say. That's not so trivial to model, basically. So like the most people who do that in literature, they use classical force fields because you need larger cells, you need longer length scales and time scales. And so that's also how we started. But you will see that it will not be good. So this is the catalyst. So this is SAPO 34 catalyst, which has also small windows. And so here we have a problem. So for example, this is propene. It needs to travel from here to here, and it needs to cross these windows. Yeah? You can see that here sometimes also Brunstad acidic sites are, of course, decorating the window. Yeah? This is on itself, it's not a free process. So this propene does not go freely from here to here, it's also activated. This is an important point to understand. Yeah? It's hindered. You can also see that by type of the dimensions. So basically what needs to happen, this molecule needs to go from here to here. So then we use these special techniques that allow us to also go from one minimum to the other minimum on the potential energy surface, and where we also have a barrier, let's say. Here you can see that we defined there's an axis perpendicular to this window here, where we have to cross. So we have to cross from here to here. So we are going to look along this axis here, this axis. Yeah. And we are going to try to construct the free energy in terms of this diffusion coordinate. Yeah, these are technical details. We are not going to say so much about that. So basically, what needs to happen is that this propene goes from here to the other side. Here we can see the Brunstad acidic proton. Yeah? At a given moment, we can also see that here an interaction will occur, and then it can go to the other side, basically. So this is basically what we need to do. So we started to do that with force fields. I will give more explanation tomorrow, but basically you can see here windows, no acid sites. Here there is one acid site. Here there are two acid sites. You see with classical force fields, everything's the same. Yeah? You see no influence of acid sites. Yeah? If you do it with quantum mechanical techniques, so DFT-based techniques, we can clearly see a difference. So for example, if here I have the red window, it's decorated with the Brunstad acidic proton, the barrier to go from one side to the other side is clearly decreased. If I have two Brunstad acidic protons, it is more decreased. So the acidity is clearly important to help the propene to go from one side to the other side. These were free energy profiles for a series of components. So here you have olefins, where you have a double bond. Here we have paraffins, we have C2, we have C3 species. If we have no double bonds, then we see no influence on the acidity, let's say. If we have double bonds, we always see an influence. So, of course, propene has more difficulties to go from one side to the other. We can see that the barrier here is higher than, for example, compared to ethene. It's normal, of course. Propene is a bigger molecule. Yeah? But interestingly, irrespective whether it's ethene or propene, we always see that the barriers are lowered when we have acid sites here. We can try to also have a look more in detail to this movie I already have shown you earlier. What you can see is when this propene crosses the window, that basically it makes a tight connection with this Brunstad acidic proton. And basically what happens is that this proton helps the movement, so my propene is basically first on one side, then the proton actually helps the propene with an interaction with a double bond to go to the other side. It's like it gives direction from one the side to the other, let's say. And that's the function of the Brunstad acidic proton, yeah, that we can see here. And you can also see it more in detail here. So basically, so we start here with this ethene, for example. It's taken by the Brunstad acidic proton, and then it travels to the other side. So it's a very interesting, an interesting example to see how we can also try to modulate the diffusion and understand the diffusion at the molecular scale. This was also confirmed by experiments. So experiments done at various institutes. Diffusion is very difficult to measure, yeah, because it's a multi-length timescale process also. Also from experiment, it's very difficult. So NMR experiments were done here. TAP experiments were done here in Oslo. And also spectroscopic investigations were done in Torino with the group of Silvia Bordera. So I'm not going to explain too much of the experimental details, but for example, here you can see the diffusion coefficient in terms of the acid site density. And this is for ethane, so no double bonds. For this ethane, we can see that there is no influence of the acid site density. If you have this ethene, then we can clearly see that the diffusion coefficient indeed enhances by having a higher acid site density, let's say, by having Brunstad acidic proton. So this confirms basically what we indeed also saw. And these are the TAP experiments where you have mean residence times in terms of temperature. We can also see, for example, here that for propene and for ethene we have higher this residence time. So it was again a confirmation. So this shows us that also diffusion we can understand at the molecular scale, but it's rather complex to model, let's say. We need very expensive techniques. And in the last few slides, I want to show you, because what we did here, we did everything with DFT here. Yeah. So this is computationally very expensive. Yeah? And so the point is that we need more efficient methods to describe the potential energy surface if we want to come closer to the experimentalists. Yeah? And so the first proof of concept I'm going to show you, which is now also out and published, is about the proton hopping process, where I'm going to do this movement. We're going from quantum mechanics to machine learning potentials. So it's a very simple process. You could say, okay, why do we want to study this? Basically, it's just a hopping from a proton from this side, to another oxygen. And you could think everything's known, because it's a very basic process. But of course, we also wanted to investigate our methods, basically. And so it was good to start simple. Although, when you look at experimental results, and you look also at activation energies for this proton hopping, measured with different techniques, so infrared and MR, so we can see that it's quite some spread on the data. So also from an experimental point of view, it's not so straight on, let's say, to know what happens. Yeah. So here our idea was to try to construct a machine learning potential. The idea was, here is that we start from underlying quantum mechanical data. We represent the atomic environment, and then we feed all this information, quantum mechanics information, into a deep neural network, let's say, and then we can also obtain energies and forces. This is, in a nutshell, what we do. Yeah? So we do not solve the Schrödinger equation anymore for the big system. We do it for some well-trained systems, and on these well-trained systems, we are going to parameterize a potential. And this is going to do things much faster. And so here you can see free energies in terms of this, the reaction coordinates, so for these proton hoppings. And so these are for with DFT. The blue curves are with DFT at various temperatures, you can see. We can see with the DFT, with the MLP, it gives almost completely the same results. And then we can do the movie again. So this is now the movie which is done with the MLPs. And an interesting thing that you can see here is that something peculiar is going on here, because you can see the proton. It apparently has some uncertainty. Yeah, but a proton, of course, it's a light particle. It can have some uncertainty also from quantum mechanics basis. Yeah, so it's not really, you cannot always look at it as a classical particle. Yeah, and so the good thing about these simulations is because we could do also longer simulations, that we could also do these simulations with path integral molecular dynamics and also simulate the quantum effects of the proton. Yeah, so this opens perspective to do new things, let's say. So this is first proof of concept, of course. We are working more. So this paper is published now, but we are doing quite some work in the group to do that. So yeah, this brings me to the question, can we understand design zeolite catalysis? So let's go back to this picture. So basically, for reactive intermediates at operating conditions, it's fine. We can do that. Yeah, so locally here, we can do that. We can also look at reactions. Diffusion, basically, I've shown, proof of concept, we can study diffusion, but it's computationally very expensive, so we need to look at other techniques to do that in a more efficient way. Yeah, so we are also going to try to also explore all these other phenomena here, all these other trajectories that you have here, because the problem that we have now, we model all these different processes with different techniques. So basically, we would need a complete technique to study this overall trajectory that the particle does when it comes from the outside, does something, goes again out. This is basically what we would want. And this is basically perspective towards the future, I would say. So ideally, we could simulate in an integrated model, when a flow of molecules come over a crystal, we could simulate all of these trajectories and simulate on the fly what happens on the catalyst. That would be great. Yeah, we are not yet there, but that would be great. Then we could merge lengths and time scales. Yeah. So let me skip this. So some final considerations. So where do we stand? Can we model realistic functional nanostructured materials at operating conditions for timely applications? So I have hopefully shown you that there are a few challenges. We need a good representation of the crystal with its defects, so it's the first challenge. We need a good representation of potential energy surface, so it's this plot. So we are working a lot here, but this is second challenge. Third, we also need good, consistent models to have this consistent trajectory and dynamics of all these phenomena. We wrote some perspective papers on that. If you're interested, you can also read there. So this is also one that's just out from this week. So challenges in modeling nanostructured materials at operating conditions. I'm going to show you one quote that I also wrote there. So basically, it's very ambitious, of course, but I think this is an important sentence. Major steps forward may be achieved from collaborative efforts from theoreticians also from various fields, yeah, but also with experimentalists. So I really think to move this field forward to design materials that we need synergies. Synergies among theoreticians, but also with experimentalists. I think that's the way forward, because we see, for example, in this world of machine learning potentials, these are developed in a fundamental field, but now we need to bring them to other fields, let's say, yeah, and that's a challenge on its own, yeah. Yeah, here you see, I want also, this is a good moment to indeed thank all our collaborators, experimental collaborators. So we have done great things together with very, very, very good groups who have helped us to understand things. And this is indeed also, this is a picture which is in the hall, in the corridor where our group is, if you once would come, once in Ghent. So this is a picture that I made a few years ago. So I went on a holiday also to the US, where we have the big sequoias, as you go, no, the redwoods. And of course, these trees can only become so big because there are interconnections, so there are synergies, basically. And this is basically also our motto in the center, stronger through collaborations in the center, but also to the outside. I think science has no borders, should not have no borders, and I think that's the way how we should proceed forward. So I think that is an interesting, inspiring picture to take along with us, and that we try to take along every day in our research, because we are a multidisciplinary center with physicists, chemists, and that is basically the way how we move along. So, and yes, so of course I want to thank the group, so the group in Ghent. It was only possible thanks to the young people. The group is only what you are, thanks to very good young people. We are nothing without good young people. So I really realized that. So they are the people who do the work, and of course I want to thank them for all their efforts, how we could proceed along the years. And lastly, I want to thank you for your attention.
Thank you very much, Professor Van Speybroeck. I think we can have a few questions. I guess there are somewhere. Yes, already one, two.
Check.
Thank you for your. Okay. Okay. Thank you for a nice talk. I have only two curiosities. The first one is related to with the nanoporous material. You know, you do very nice simulation in two different, means MOF and zeolite. And what happened with the most usual? This is the activated carbon. Is because it's more complicated to do simulation. It's only curiosity.
Yeah, it's indeed also more complicated, often also to determine the structures. We have never worked on it. Yeah, I know some colleagues in Ghent experimentally work on it, but we have never worked on it. Because, of course, you always have to start from a good starting structure. So, so we never did work on that. But it's, for some materials, it's very complex to indeed start from very good structures also. Yeah, so, that's the short answer. Yeah.
Another curiosity is related with the mechanical properties.
Yeah.
I mean, when you apply, when you say realistic material, I think when you're looking for defect, it is looking for defect. In the case of working in chemistry, means you do catalysis, the defect is very important for application. But in the case of the mechanical properties, I think the most important defect is dislocation. Means if you want to do something related with the mechanical property, I think you must be introduced not the typical defect you have when you talk about chemistry, catalysis, or something like that. I think it's more proper to introduce dislocation. It's the people do usually in metallurgy. Thank you.
Yeah, of course, here we have specifically looked at the potential to store, let's say, mechanical energy into these materials because they have these typical properties that they can contract, have huge contraction. You can store mechanical energy. Of course, when you go to realistic material, of course, there will be quite some other effects, of course, also, as you say. But the reason why we looked here is because they have the specific property to store this mechanical energy originating from the pores, let's say, and going to the other phase, let's say. This is the reason why we did that. But of course, if you go to realistic materials, you want to have realistic applications. We need to look also at bigger systems and see what kind of defects and dislocations. We need to study that more from a holistic point of view, as I would say. Yes.
Thank you, Veronique, for a very nice talk. You had one side remark that sparked my question. When you went from the smaller to the larger systems, and then you said, then it's a bit similar to biochemistry and the large system. Can you expand a little bit on the similarities and differences between simulations for those?
Yeah. Yeah, it's interesting. It's very interesting. So, of course, there they have done a lot of simulations on very big systems, with force fields, also with coarse graining, for example. They also do a lot of coarse graining. So we have also tried, and actually in the field with us, it's not so, you do not find so many coarse graining efforts, basically, because there you also lose the time dimension. It's difficult to also properly define the beats, so it's not well developed in our field, I would say. Yeah. Then regarding, of course, the time scales, they have the same problems with these length and time scales, of course. And a lot of the techniques actually that we are using come from the biochemical simulations, like with the enhanced sampling simulations. If you look into the literature, it was first there. Yeah, and then you need to port it to our system. But it's not always just a matter of just using the method from the other field here, like, for example, with the force fields. So like with the big system, we use the OpenMM program, which is, of course, very much known in the biochemistry field. But like, for example, to port our force fields to that OpenMM, we really had to do method developments. And like, for example, also for the materials, if you want to have this, these phase transformations, you need particular ensembles, barostats also, to allow these variations in shape of the material. So we also had to implement new barostats. So it's not always just using the techniques they already do there. You always need to adapt also. Yeah. So that is indeed what I have seen. Yeah.
Do you think you can go back then when you have all these metals in there and make use of those developments for the biochemistry field?
So the metals, of course, we can also have here metals in our field. So, but I'm not fully following your question.
Because you showed quite a few metals there.
Yeah, that is, of course, yes. So there's the simulation of metals, and like, for example, I did not show it here. Metal-loaded zeolites, for example, it's very complicated. Yeah. To a first instance, when you start with it, that you know what the active site is, for example. Yeah. So that is my experience. Of course, yeah. Then you need, So then you also need this close synergy with the experimentalists, basically, to try to unravel what the active site is. We had some problems also when people approached us, experimental people approached us, and say, yeah, can you solve this? So I had a collaboration, for example, also with a group in Leuven on palladium zeolite catalyst for CH activation. So we worked for 2 years to already know what the active site was. So that is a very complicated story, I would say. But there I think we would also benefit from techniques, layer techniques, because there in the center the active site needs to be described very accurately, quantum mechanically, to have the different also oxidation states and spin states and so on. And then it might be good to have other layers. So also that is also done, of course, in the bio field. It's also done there. The QMM approaches, of course. We do not see in our field now so many QMM good interfaces to do that. I think there is interesting work to do there. Yeah.
Thank you very much.
Yeah.
Okay. Any more questions? I see a hand over there. Yes. Finn?
Okay, you talked about force fields a lot, and I have some idea what it is, but why is it a problem? I mean, what is the problem with force fields? Because there are many different, and one should believe from a stupid background that one force field would be enough, but it's obviously not.
Yeah.
And so what is the general problem there?
Yeah.
Is it the description of the atom itself which is...
The problem is, so what you do with force fields is, so basically you describe the interactions between the atoms by very simple analytical functions. This is what you do. Like, for example, if you have a spring, 2 atoms, like, for example, you describe it with this very simple harmonic oscillator, let's say. And so you predefine this interaction. There are parameters. These parameters are parameterized sometimes to experimental data, to underlying QM data. And the problem is they do not have the transferability. For example, if they come in another environment, like, for example, the spring, it cannot break. It cannot break. Yeah. So basically, you predefine too much what happens in your system in advance, yeah? And so that is the difference with the machine learning potentials. This is also a force field. In a way, it's also a force field. It's a numerical potential, yeah? But with many more parameters from underlying quantum mechanical data. And the idea is if we parameterize it right, yeah? Because the machine learning potential will only give you what the outcome will only, you need to train it. So you have to feed the machine learning potential. So if you do not give the right data, it will not produce the right data. It's very dangerous too. It's very dangerous too. So basically, but the idea is if we train it correctly onto a lot of circumstances, it will mimic what the Schrödinger equation does. And so there, for example, we can break bonds, yeah? And we can bring it in different environments. That would be the idea. And that is something we cannot do with the classical force fields. That's the problem, yeah.
If I don't see any more questions, so I would like to ask you to join me again to thank Professor Van Speybroeck for a very exciting and inspiring lecture. And actually, on behalf of the chemistry department, we also have a token for you that is the dissertation of Professor Hassel, who has been printed in only 100 copies, and this one is copy number 71.
Wow! Thank you, thank you, thank you. Yes, it's a very nice gift. Thank you so much. Thank you so much. Yes.
So thank you very much for being here, and thank you for the audience online. Unfortunately, you don't have the possibility to participate orally, but I think you enjoyed the lecture as much as we did. There will be an extra Hassel lecture tomorrow, a more specialized on theoretical chemistry, and that will be at the chemistry department tomorrow at 11:15 as well. So thank you very much for your attention, and see you tomorrow. Bye-bye.